2.5 in just 1 second. But first of all, 2.4. We're transitioning color pens, homework spirals. Homework pens, color pen, and homework spirals. What color should you never be grading in? Yeah, black or gray. Yeah, probably not wise. What if you get absolutely everything right in your homework? Show me like a -0, show me a star, show me a, I did a great job, show me a check. I got 100%. Because otherwise, when I grade your homework spirals, I have no clue whether or not you truly graded the assignment or whether you just skipped it, unless you show me like, hey, I got 100%. But if you guys are getting 100% on every single homework and all the evens, maybe you should be grading your odds the night before in a colored pen also. Because maybe you're making mistakes the night before, but figuring out how to do them correct and then being ready, being good on the evens. But it's very rare. Chapter through. So I don't like taking homeworks or points off of homework for something as silly as not grading. So show me that you're grading. Here we go. Number 6, complex conjugates. In class, we just called them conjugates, but they were conjugates of complex numbers. So hopefully you guys figured that one out. Number 8 was so easy, it was hard for some of you. How do you fill in? Well, what's in the A spot? 13. Oh, what's in the B spot? 4. That was it. That's all you had to do. Number 26. Did you guys kill any seals or did you keep it legal? -3 minus 11i. How's our mental math doing? We doing okay? Number 40. What am I going to tell you not to kill? Seal is distributing. Puppy is foiling. So you had to foil, and you ended up with 25 minus 20, 40, minus 20i, minus 20i is minus 40i, and then 16i squared. Sorry, it's a struggle today. Wait, where'd the I squared go? Ah, it's a -1, and then 25 minus 16 is 9. Dun, 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 dun. Make a note of it. Make a note of it. You gotta. If puppies are your weakness, it's okay. You just gotta make a note of it and say, I need to work harder. Write it out every time. Whoa, what's going on in number 72? X equals -b plus or minus square root b squared minus 4ac all over 2a. But was there another way to solve this one? You could have completed the square. Did anybody complete the square? Tony did. Did it work? I'm not saying you had to complete the square. I'm just saying you could have completed the square. Remember, the quadratic formula is really just completing the square in a simplified form. So you could have just done. I'm just showing you in case some of you, okay, let's be honest. How many of you guys, the very first day of school, remembered the quadratic formula when you came in this class? Wow. That's a really high percentage. I'm impressed. I mean, this is honors. That's true. Which means that a lot of you guys are probably pretty good at memorizing. Just, I'm impressed it stuck around like over the summer. Okay, so maybe you guys don't need it as much, but it's very typical for kids to be like, well, I should know it, but I don't. So what you could do, and some of you are like, well, I wouldn't remember the completing the square any better. Well, okay, maybe not. But you could plug in, you would end up with x plus 3 quantity squared plus 1 equals 0. Could also complete the square and get there. Wait a minute, why is there an I? Because it's square root of a -1. I mean, up here you actually would have gotten square root of a -4, which would have been 2i. But couldn't you factor out the 2, which is the only legal way to simplify? If you did this, check it. If you got it wrong, if you did that, you killed a kitten. You can't just take away 2's because you want to. You can only take away 2's if you can divide everybody. You got to distribute the division just like you distribute multiplication. So this guy has to be divided and that guy has to be divided, or just think factoring out. Dun, dun, dun. You guys have to choose a way, quadratic formula or complete the square. Choose a way, stick with it. Train your brain to always be ready. Oh, is that the last one? 98 was an extra credit. I'll peek at it. I don't want to show the full solution because then someone could be like, I didn't do it, but I'm going to sneak it real fast. For those of you guys that did try number 98. didn't want to show the full solution because I didn't want to give anyone the opportunity to be like sneaking it in under the radar. Oh, actually, we just turned to it here, huh? Go team, go. Go team, go. There we go. Number 98 was a how do you see it, right? Oh, that didn't work. Okay. I'm going to go fast. You guys who did number 98, what did I map to? Wait a minute, did you guys figure out the graphing system? It's really weird. These are the real numbers. X is the real number part, so it's the A part. X is the A part. B is the imaginary part. Okay, sorry, go ahead. So number 1 was what? Number 2 was what? F. F. Number 3 was what? Because you have to go positive, positive, first quadrant. Good. Number 4 was what? Positive, negative. Good. Number 5 was what? A, because it's negative, positive. And then 6, C. Negative, negative. Interesting how they graph imaginary numbers, huh? Reals and imaginaries. X's and Y's. Okay. I apologize for getting distracted by that. Did you guys have any questions on evens or odds besides that? Robbie? 53, 61? Okay, so let's start with 53 real fast and then go to 61. But real quick, while I get there, and take a picture of it so that I can work with it, because it's having issues up here. Stand up, turn around twice, give someone a high five, then sit down. Go! Susan Simon says, this is me telling you, so obey. Turn around twice, give someone a high five, sit down. So you guys are rubbing your eyes, the air isn't on yet, and it's a struggle. Wait, pause! Wish someone happy Friday.
Happy Friday.
It's Friday.
Game day.
Friday, game day, Valley. Go team. All right. Here we go. Shoop, shoop. That didn't work.
Oh, wow.
Yeah, I don't know what's going on. Okay. Robbie, 51. It's a division-y one, right? Okay. We're trying to write it in standard form. Guys, help out real fast. Help us all out. What's standard form of a complex number? Yeah, we're trying to write it like a plus bi. The problem is, it's not an a plus bi. It's an a over I. So what did we learn yesterday that we could actually do to this guy in order to get it to that form?
It's conjugate.
Well, conjugate, but it's I plus 0, so it's I minus 0, which is still just I. Why does that help everything? 3i, and there's an I squared, and what does I squared substitute for? Oh, so it's the same thing as 0 minus 3i, or just negative 3i. Dun, 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 dun. Yeah. Oh, I'm sorry, I took the picture of the wrong one. So 53, was he a conjugate one, Robbie? Why am I saying conjugate one? It doesn't just have an I or a multiple of I. 52 is similar because it's a 2i. You can still just multiply by I over I, but as soon as you have a plus or a minus, you have to do a conjugate. Like the vocab term in number 6, complex conjugate says take the complex guy and make a plus. But Robbie, check your work real quick. Did you put parentheses around these guys? Why is that important?
Yes.
Maybe you still distributed correctly, but maybe you messed up in the distributing. Because with the parentheses, you would have remembered, hopefully, to distribute the 2 and to also FOIL this guy. I'm going to do it the long way just to make sure that everything is legal. So you have first, outer, inner, last. The outers and inners always cancel with conjugates or differences of squares. You just told me what I squared was, right, Robbie? What's I squared? So a negative 25 times a negative 1 is a plus. It wasn't super nice because it ended up being 40, right? What happens when you divide 8 by 40, distribute the division, and 10i by 40? Well, it's not pretty, but what ends up happening? Oh, gracias. That's even worse. That would have reduced a little bit. Does this reduce at all? Huh. So, I mean, technically for standard form, you wouldn't put the I in the numerator. Technically, the I would be his own little separate dude. 10 over 41 would be the coefficient. I would be over there. But Robbie, it's all we can do. Dun, 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 dun. I know. Hang in there, Jaden. Air should be turning on soon. And then Kathleen and Robbie, it was 61, right? Ooh. Look at me getting sneaky and throwing a fun one in there. Guys, I see two fractions, and I see them being subtracted, but you guys should know from your previous math training that we can only subtract or add fractions when they have like or common denominators. So, can we add or subtract anything to make those denominators the same? No. But what can we do? Multiply. Remember if you have something like 1/3 plus 1/4, we multiply him by 4 over 4 and him by 3 over 3. Very, 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 very similar idea mathematically with these two. That's a 1 plus I, which is totally different from a 1 minus I. Similar, but different. So I'm going to multiply it by each other. There's a party going on in the hallway. 1 minus I over 1 minus I. It ends up being the conjugate, but I mean, well, I guess that's the conjugate too. Was there any that weren't conjugates? I don't know. Why am I putting parentheses all over the place? Because I don't want you killing any seals. Ooh, why am I putting parentheses? Oh, yeah, it's a minus. I have to be careful with minuses. What ends up happening when, you guys already did this, right? When you multiply 1 minus I times 1 plus I? Don't you get 1 minus I squared? And then, yeah, I squared is a -1, so that'd be 1 minus a -1, or 1 plus 1. Isn't that just over 2? And they combine because they're like denominators. Then I get 2 minus 2i minus 3 minus 3i. I end up with a -1 minus 5i all over 2. And then, Robbie, it's like the one we just did where it's not super pretty, but you still have to split it up. So it'd be -1/2 minus 5/2. Is that good? It wouldn't be in standard form. But if it was like a multiple choice question on a test, I bet you could make it match. Does that make sense? So your answer wasn't wrong, just your form wasn't complete. I'll put it that way, Kathleen. All right, are we good? Any more questions going once? Yeah. Going twice? Sold, 2.5. Guys, today is a monumental day. We've been working towards 2.5 for a while now. Like, I've been alluding to it non-stop, but some of you might not have realized it. I've been alluding to this guy for quite a while. Not like in chapter 1 quite a while, it's a little intense, but in chapter 2 quite a while. Now, section 2.1, what was the type of polynomial we were dealing with? Like, what's the most basic curvy polynomial? Not a line, a quadratic. So 2.1 was his own deal. We were just talking about quadratics, standard form with the vertex HK, completing the square. So section 2.1 was just quadratics, just the most basic guy. But 2.2, 2.3, 2.4 we're all building up to today. 2.3, 2.2, 2.4 we're all building up to today. Hopefully some of you guys have already gotten this written down. Just a few of you are still needing to write it down. Here's the idea of the fundamental theorem of algebra. Sounds kind of important, right? Fundamental theorem of all of algebra. Now, this comes from the fundamental theorem of algebra. This might not be it in its entirety or in its only applicational form, okay? So I'm not simplifying this huge fundamental theorem of algebra saying, oh, this is it. This is the only thing. Okay, but this does come from there. Polynomials of degree n have n complex zeros. Wait a minute. That's different than we learned. Didn't we learn that an nth degree polynomial has at most n zeros? At most? What's this one say? Has n zeros. No. That doesn't make sense because we talked about a parabola. A parabola has a degree of what? 2, right? And didn't we talk about how it doesn't have to have any zeros? Here's the x-axis. Here's my parabola. Is it going to, I can't do it without my arm being there. That's okay. Is this going to hit the x-axis at all? So we've already disproven the theorem. Okay, well, they didn't know what they were talking about. Oh, they were way smarter than we were. Pause. I want you to go back to section, where did we talk about at most? I think that was section 2.3. Go back to 2.3 where we talked about having at most n zeros and at most n minus 1 turning points. Remember that part? And I want you to answer for me, was there a word before zeros? Real zeros? Whoa. What's this one say? Complex zeros. We're not just talking about real anymore. We're not just in Kansas anymore. We got to deal with real and imaginary. Section 2.5 says we're going to find all the zeros, the real ones that we can see on a graph and the imaginary ones. Yeah. The real ones and the imaginary ones. And here's the struggle, guys. Your graphing calculator will only show you what zeros. Ah. So you have to know how to find the imaginary ones by hand? Struggle. Aiden, go ahead and stand up, bud. Just stand up. It's okay. Shake it off a little bit. David Rosso has to do it. So does Michael Schweitzer. Just stand up. Sometimes it just gets rough. You have the sun shining on you. I know it's a struggle. So guys, I want you to figure out and solve for the zeros of A and B. And if there's a C, solve for those zeros too. How do you solve for zeros? Set what equal to 0? The function or the y value, right? The function or the y value. Kyle, I'm listening. Go ahead. What was your question? Discriminant. But only for quadratics, sadly. Just in case it gets bad again, the podium's waiting for you. David's used it a few times. Just don't lean too heavily on it if you end up, because it's bad.
Really wake you up.
Yeah, I've been sitting up here and I've been leaning on it when I'm like, whoo. I haven't actually face planted yet, but it's been close. Okay, did you guys do it? Okay, keep going. Find the zeros. Set y equal to 0. Set y equal to 0, Robbie, solve. Set y equal to 0 and solve. Find me how many zeros. Looking at it, there should be 1 of the first, 2 of the second, and 3 of the third, according to the theorem. Looking at it, there should be 1 of the first, 2 of the second, and 3 of the third. Let's see how many you find. But they could be real and or imaginary. Does the math find them for us? My turn. Can I start playing? You guys keep going. I'm just going to catch up. Do you guys find the imaginary ones for the third one? Because this section says don't stop just because it's imaginary. Actually find them. So we would subtract the 4. We would square root both sides and say, well, we can say it's 2i, and you're right, plus or minus 2i. How many zeros did the first ones have?
1.
How many zeros did the last one have? 3, plus or minus, right? 1, 2, and 3. How many zeros? Okay, wait, 3, 3, 1, 1. Oh, it's 2, but they're combined in 1. Wait. How do we deal with this one? How do we say that it's still okay? Yeah, it's a multiplicity of... Oh, there are 2. It's just the same. There are two. It's just the same. The parabola is bouncing off the axis at 3. Robbie.
How'd you find the first zero for C?
Oh, I set, when you look at this, when I pull out a GCF, I have to set him equal to 0 as well. Even though he doesn't have two terms, he's still a factor. So I have to set both that guy equal to 0 and that guy equal to 0. Is that cool? Yeah. Because if x was 0, that works. But also if x was plus or minus 2i. Cool. All right, so even though this theorem is true, can it sometimes look not true? Yeah. So does this mean that there are n x-intercepts? No. But what it means is when you factor completely and put together all the real and the imaginary and thinking about the multiplicity, you will find n zeros for every single polynomial. So we know our goal for today is to find all the n zeros for whatever we're being given, we've been given. But here's a problem. Now that we've learned synthetic and long division, we're not just going to be given ones with GCFs. Oh, what am I talking about? Now that we've learned synthetic and long division and how to go looking for factors in harder polynomials, cubics, quartics, etc., we're not just going to be given ones like section 2 that had GCFs. 2, they always had GCFs. We got to pull it out, get a quadratic, and then factor, or use the quadratic formula. But now they're like, we're giving you more realistic ones. So we're going to have to use the idea of the rational zero test that says some of our zeros won't be nice numbers. Some of our zeros may be fractions. And we wouldn't naturally think of trying fractions in the x method, because that makes life a whole lot harder. So instead of doing the x method with fractions, we're going to use this rational zero test that says any rational zeros, any nice zeros, fractions, negatives, positives, whole numbers, any nice zeros can be found from the list of plus or minus all the factors of the constants paired with all the factors of the leading coefficient. So the steps is form a possible list, and then trial and error, either by plugging in and getting 0, or by using synthetic division, remainder 0. The way we can find the actual zeros is either by plugging in, getting 0, or synthetic division, getting a remainder of 0, which we practiced in section 2.3. And if you plug in, it's not 0, it's not going to be a solution, so don't use its factor. Try something else. If you do synthetic division, the remainder is not 0, it's not going to work. Try something else. But first, we form a list of all the possible, using this little pattern up above from a snazzy rational zero test that we're not going to go through really in more detail. So first, we list all the possible, and then we start trial and erroring the actual. Now, this section actually says there's some strategy as to which ones you try. Sometimes we just plug in the really easy ones because it's like I can do that pencil math and know really quickly whether it's 0 or not, whether the value is 0 or not. Some of you realize synthetic division is sometimes easier than plugging in section 2.3, so you can do synthetic division maybe even faster than plugging in to know whether the remainder is 0 or not. But there are some other tricks at the very, very end of this section, none of which I think you have to memorize or I'm going to force you to use like on a test. But they can kind of shortcut the process and simplify the process just a little bit too. And IVT is going to come back, because we can always narrow down the range of a 0 if we plug in and see a sign change in the F. And be like, hey, there has to be a 0 somewhere. Hey, which of these possible ones fall in between those two numbers? Huh. Ready? Let me dual page. A few of you guys are still writing. And that's okay, there's a lot of words on here. But I want to get to, an example. Why is he harder than any of the ones we've seen this chapter as far as factoring from scratch? Yeah. What degree does he have? 4. How many terms does he have, added or subtracted? Lots. And what's not present? A GCF. Oh. Oh, but wait. What do we know? Directions. Sorry, find the rational zeros. We could try grouping, but how does that... And grouping doesn't always work anyway. It only always works with the modified x method, sadly. Well, we know how many zeros he has to have. How many complex zeros are we looking for? Start, but that doesn't really give them for us, does it? It just tells us how many. So what's this whole thing over there? Steps. Number 1. What zeros are even possible? What nice zeros? What rational zeros? If these are all complex, we're in some pretty big trouble. Hopefully there's at least 1 or 2 real ones. Hopefully. Is it possible for a fourth degree to have zeros? Yes, and then we're in trouble. But hopefully this one has at least a few. Actually, if you guys want to see a few, just real quick. Question, can this polynomial, my mental mathers, help us out. Can this polynomial be a positive number? Can it be a negative number? Let's start there. What do you guys plug in first? What's the easiest number to plug into any polynomial? Oh, I was thinking 0. What happens if you plug in 0? Ah, this can be negative. Cool. All I need to ask you is, can this be positive? And if it can, it has to have at least 1 0. Does that make sense? Negative to positive? So can it be positive? Plug in 1. 1 minus 1, 1 minus 3. Oh, that's negative 2. Also. We'll plug in what? 2? Plug in 2. 2 to the 4th is 16. So right now I'm just trying to see if there are any possible real zeros, because if I can't find any, I'm in trouble. So we just figured out that f of 0 is a negative number. And f of 2, I have 16 minus 8 plus 4 minus 6 minus 6. I have 20 minus 14 is 6. 6 minus 6 is, oh, just found one. If I plugged in 3, it'd be a positive number. Okay, well, we kind of just cheated and found one without even meaning to. But hold on, let's first of all talk about how could we have gotten to 2 without just randomly plugging in numbers? Because that's not always safe. Here's what this means over here. Plus or minus all the pairings of all the possible factors of the last. 1, 2, 3, and 6. And all the factors of the first. 1 and 1 and 1 and 1. And then you make all the different pairings. So what's 1 over 1? 1. What's 2 over 1? 2. What's 3 over? Okay. How many different possible nice zeros are there? 8. We could try plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Could we do synthetic division with positive 1, negative 1, positive 2, negative 2, positive 3, negative 3, positive 6, negative 6? Yes. And the zeros, which lead us to factors, would be any ones whose remainders are zeros. But what was even faster, at least for the small numbers, than doing synthetic division? Plugging in, plugging in. Now, could 0 have been a 0? No. I was just looking for a sign change. But what would have happened if we had actually plugged in? Wait, we did plug in 1, didn't we? But didn't we realize that 1 minus 1 plus 1 minus 3 minus 6 ended up being not 0? So we moved on. Well, and it was negative, so it didn't even tell us anything. Negative to a negative, and it's not even a 0? Well, okay, forget positive 1. Could we have tried negative 1? I guess, if you like it more than trying 2. Some people try all the positive numbers, then go back and try the negatives. Some people stick with the small numbers and work their way up. Or try a couple positives, then like, bummer. Try a couple negatives and then move to the higher numbers. Either way. Robbie? Oh, 1 to the 4th is 1. 1 cubed is 1. 1 squared is 1. 3 times 1 is 3. And the 6 was right. I'm plugging in, plugging in. If I plug in negative 1 to the 4th, isn't that a positive 1? What's negative 1 cubed? Minus a negative. What's negative 1 squared? Positive. What's negative 3 times negative 1? What's, oh, I just found another one. Austin, what's up? Oh, I asked myself, what are all the factors of the constant term, aka of the last term? What goes into 6? 1, 2, 3, and 6. That's it. And then I asked myself, what are all the factors of the leading coefficient? Just one. So 1 over 1, 2 over 1, 3 over 1, 6 over 1. I took all the possible pairings. And that's how that box works. So I tried 1. It was a no-go. I tried -1. Well, so far, I've found 2 zeros. I think I'm doing pretty well. What do you guys think? So I have -1, that's a winner. I have 2, that's a winner. Wait a minute. Hold on. In section 2.3, if we found a winner, could we break down a polynomial with synthetic division? Yeah, we can. So why aren't we doing synthetic division and breaking them down? Let's get this 4th degree cut down to size, something that we can deal with by hand. So I'm going to go ahead and put that 4th degree. Let's see, what are the coefficients? 1, -1, 1, -3. Zeros, right? Because I have everybody. You guys choose. We have 2 different ones to choose from. Do you want to put 2 in the box first or -1 in the box first? We'll do 2 because no one's saying anything. It's the first one I found. Okay. Go ahead. Do synthetic. You don't need me for that. You can check with my work that I'll start in about 15 seconds. Go ahead. Bring down the 1, hopefully, right? What happened? It's okay. Where did I make my mistake? Good. Good. The remainder doesn't match the function value. I did something wrong. Because remember the theorem from 2.4? They have to match. Why is it really, 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 really good that I found another 0 also? Why not just stop and say, oh, hey, I know this guy. This guy comes from an x minus 2. I know a factor. Why wouldn't I just say, yay, let's rewrite? Uh-oh. Is this one I can do by hand?
Yeah.
By hand? So you can go ahead and do parentheses for me? Maybe if the grouping works, but I just said a second ago what doesn't always work. If we haven't done an X method to get to an answer, grouping doesn't always work. So even though this one actually grouping could work and we could do it by hand, didn't we find 2 zeros? Guess what? We can go, ready? Again. We can go again. I'm going to put that -1 in the box and say, hey, I know another one. Ready, set, you guys get ahead of me while I answer Kim's question. But do synthetic division again. That's a cubic. I don't like cubics. Let's go down to a quadratic. Then life is easier. So we plugged in 2 and saw that it was a 0. I knew it was going to work. I was like, sweet, let's divide by 2. I'm going to go close the door because it's starting to cool off in here, yeah? You guys are synthetic-ing. Is that a verb? I don't think so. Synthetic dividing? Performing synthetic division? That sounds best. Hold on, pause. Sam. Well, because I was lazy and so I was starting with the little baby numbers. I did trial and error, which could have been 8 different synthetic divisions, but I was way lazier than that because these are small numbers. Like, I think it's easier for me to plug in and see if it's 0 for the small numbers. If we get stuck and if none of these got to be 0, well, A, we could have made mental math mistakes. But B, maybe all the zeros were up here. I probably would have done synthetic division for these just because my mind doesn't always perfectly do great mental math if I'm plugging in lots of big numbers, raising them to the 4th and 3rd powers. So yeah, I was doing my trial and error step. And we were lucky because our little baby numbers were working. I'm going to go ahead and do synthetic division as I answer Kyle's question. Go ahead, bud.
So if we put in another 0, which was -1, would we use the one we got from the answer, or would we have to restart from the original problem? Could you just use
We could actually do either. Because we don't have to go back to the very beginning if we've broken him down, because we're looking for now the zeros of this guy, which will also be the zeros of the original, but you could simplify your life a little bit by only looking here. Because for instance, right now, once I've broken this guy down to this, couldn't I automatically work because those are both factors? Now I just have plus or minus 1 and 3 and plus or minus 1. So I can actually, once I get here, I can come back and I can say, well, neither of those work now that I've taken out a 2, because this guy remaining, if I look at his last term over his leading coefficient, you want to think about it, this is the factors of the last over the factors of the first when it's written in descending order. That would just be plus or minus 3 and plus or minus 1. Forget the 2 and the 6. They're not going to work past this point. But we already found negative 1, so we already plugged him in. And now we can go ahead and take all of this and say that was an x minus 2. This is an x plus 1. And now, guys, don't I have somebody I should be able to deal with? It's a quadratic. I can deal with that. So what we've done is, using that process, we've gone ahead and figured out that original nasty polynomial can actually be rewritten as the following. We can say that he's the same thing as x minus 2 times x plus 1 times x squared plus 3. So what are my zeros? Set him equal to 0. 2 real that I found just by plugging in. It was super nice. They were super small. And 2 imaginary. So I'm going to get x equals 2, which most of you can see. X equals negative 1, which most of you can see. And x equals, can you see it? Plus or minus square root of negative 3, which is plus or minus root 3i. I can't square root 3, so he's stuck. But the I sure can come out. And I'm down to my 1, 2, 3, and 4 zeros that I was looking for the whole time. Kim, what's up, kiddo? Oh, I was plugging in 0 at the very beginning because I was telling you guys how fourth degrees technically don't have to hit the axis. Since they don't have to hit the axis, I'm like, oh, stink. Can he be positive and negative? Because if he can be positive and negative, he's going to have to hit the 0 somewhere. So I was going back to IVT before I even started all my process. That was just to tell you guys that some answers existed, some real answers existed. But as long as you know some reals exist, there's a sign change, go looking for them with that. Yeah. Kiddos, this homework is not due until, Tuesday. So we're going to finish it up on Monday, but you guys should be able to get a really good start in over the weekend, okay? See ya. Happy Friday, football guys. Have a great game tonight. If anybody makes the trek, cheer them on well. Bye, Tony.